Okay, so this chapter involves something called triangle centers. And there are 4 of them we're going to learn about. We're going to get all 4 done today. Usually I would break this into 2 parts. We do 2 today and 2 tomorrow, but again, we're going to cover both sections today. And so I'm going to bombard you with a bunch of information. Even though I'm not going to post the homework today, I will post a summary sheet that has a lot of the stuff we're talking about today on one nice reference sheet, so you can refer to that as you're working through it. I'm not a huge fan of memorization, so I'm thinking that as you work through the chapter, the more work you do and the more of these problems you work through, the ideas that apply to each of these centers will become second nature to you. Okay, so we're going to start with a perpendicular bisector. We know what a perpendicular bisector is, right? What is it, Matt?
It's where one line.
It's a line, good. First of all, it's a line. Go ahead.
It bisects another line that makes 2 right angles.
Not bad. One small misspeak, if that's a word. What did he say wrong? Natalie?
It's bisects the base. Bisects the base, not just a line.
Getting warmer?
Isn't it the midpoint between the 2 base angles? Like it splits it into.
You're thinking triangles. Forget about triangles for a second. Okay. Say what you said again. It's a minor point, but it's really important.
One line
Good. I'll give you that.
is perpendicular to another line and creates 2 right angles.
Good.
Makes 4 right angles.
Not bad. But again, what did he misspeak?
It would be that it's like intersecting a line segment.
Good. Okay, so think about it. You said a line that is perpendicular and bisects another line. You can't bisect another line because it goes on forever. How do you fold something that goes on forever in half? So we're going to be bisecting a segment. Other than that, it's great. Perpendicular bisector, 2 names, or 2 words. It's perpendicular and it bisects. So it's perpendicular, meaning it forms a bunch of right angles, and it bisects, which means it cuts it exactly in half, which means it would go through the midpoint. Okay, so here's the perpendicular bisector. This white line is the perpendicular bisector of this segment AT. Okay. We'll get to the bisector theorem in a second. It's perpendicular and it bisects, chops it in half. And as somebody already mentioned, that special point then, I think this was you, Jalen, said that that would be the midpoint, yes?
Yeah.
Okay, good. So we're good on perpendicular bisector, right? Most of the time it will be a line, sometimes it'll be a segment, but it's always a segment that's cut in half. Think about it this way, you can't fold a line in half. You can't fold a ray in half, you can only fold a segment in half. And that transitions us to the perpendicular bisector theorem. So now we take this perpendicular bisector and we put a point on it, I called it C. The theorem, it's a reversible statement. I gave you both versions of it. And it says simply that if it's on the perpendicular bisector, then it's got to be equidistant from the endpoints. In other words, AC is equal to CT. The opposite is true, that if you have a point that's equidistant from the endpoints, it's got to be on the perpendicular bisector. Okay, does that make sense? What kind of triangle then is CAT? Tom?
Right? No. Isosceles.
Good, it's isosceles. If I take this point C and I slide it along this line, these 2 segments are always going to be congruent. They'll just get bigger and smaller. Even if I slide it down to that point of intersection, it's still going to be congruent because now we're talking about the 2 halves of the segment. Yeah, but that wouldn't be very exciting. We wouldn't have that picture. Okay. Because this is a building process, it's really important that everybody understands the perpendicular bisector before I move on, because it's going to ramp up quickly. Are we good with this? Okay, good. So now, putting this in motion, don't write this down. It's a really, really simple example. I just wanted to make sure you understand that. Here's my starting information is the yellow tick marks and the yellow perpendicular. So what this establishes is the fact that the red line is the perpendicular bisector. Everybody with me? if it's the perpendicular bisector, then any point on it, in this case R, has to be equidistant from the endpoints. In other words, 2x plus 3 equals 4x minus 7. Solve for x, plug and chug. Okay? I just wanted to make sure you understood that. I want to get into the more interesting stuff in a second. All right, now, here comes the fun. So now we go with a triangle. I took a triangle and I started with the triangle ABC. And let's start with segment AB. I took one side of the triangle, AB, and I drew in the perpendicular bisector. Now, I only have a segment here, but it would actually extend into a line. I just didn't want to clutter up the picture there. Which means in this case that AE equals EB, and that angle, which is already marked, is a right angle. Okay? Then I come over to the side AC, and I did the same thing. I drew the perpendicular bisector, which is the blue segment. It would be a line, but again, I just did the segment. Then did the same thing for BC. A weird thing happens. When you draw all three when you draw all three perpendicular bisectors of a triangle, they will always meet at a point, and that point is called the circumcenter. I'll show you a demo of this in a second. For now, we're going to ignore the yellow segments. I'll explain those in a second. Okay. So again, if I draw in all three perpendicular bisectors of any triangle, they will always meet at a point, which is called the circumcenter. So this is a new term here, point of concurrency. I will frequently call that a POC. That's what we're going to be talking about in this entire chapter, points of concurrency. Question?
Wait, so what are the blue? It's just showing it those right angles.
Yes. All right, we good so far? So that's how you get the circumcenter. You intersect the perpendicular bisectors. The reason the yellow segments are on there is because one of the properties of the circumcenter is that it's the point that's equidistant from the vertices of the triangle. So I started with the powder blue segments. That gave me the circumcenter, which I labeled P. And one of the properties of P is that it's now equidistant from all three vertices. So PA, PB, and PC are all congruent. That, by the way, is the first property. It has a second property, which, if we had more time, I would allow you to discover, but I'm just going to tell you. If each of these segments are congruent, I can draw a circle with this as the radius. Let's say PA is the radius. Are you with me? And if that circle starts at P at the center and goes through A, hopefully you see that it would also go through B, because that's the same distance, which is the radius, which means it would also go through C. So the second property of the circumcenter is that it's the center of the circumscribed circle. I'll give you that once more. It's the center of the circumscribed circle. What does it mean to circumscribe? You all have English. What's the prefix circum mean? Around. And scribe? Right, or draw, yeah. Circumvent, circumcenter, circumscribe. Okay, now here's the question. Well, there's a lot of questions here. Let's go back to this triangle I had here. What kind of triangle is that?
Scaling.
Might be scalene, we're not sure. Think about angles more. It's a acute triangle, okay? And in an acute triangle, notice where the circumcenter is. It's inside the triangle. What happens if I change the shape of the triangle? What if I all of a sudden make that an obtuse triangle, or I make it a right triangle? Where will the circumcenter go, Tom?
Outside of the triangle.
For which one?
Obtuse.
Yeah, if it's an obtuse triangle, it goes outside the triangle. Okay, what about a right triangle?
On the triangle.
Where on the triangle?
Line 7 is
I don't know if I understand.
What's
On the
the
hypotenuse?
hypotenuse, I think it's called, yeah.
Where on the hypotenuse? Anywhere?
The midpoint.
Ooh, let's see if she's let's see if him and her are correct. There we go. Okay, so here's a triangle. How would I get the perpendicular bisector? Well, the first thing I need, it would be nice if everything went this easy, but I would need the midpoint. So because of this program, I can just click a button, the midpoints appear. Then I need the perpendicular bisectors. So the perpendicular bisectors go through the midpoints, and so there are the perpendicular bisectors, and verifying what I already said, they're going to meet at some point called the circumcenter. Now, the cool thing about this program is I started with this triangle, which is an acute triangle. I can then grab this point. Well, let's show the circumcenter there. There's the circumcenter. I can grab this point and drag it around. So if I make it an obtuse triangle, Tom was right, it moves outside the triangle. So in your notes, what I want you to write, though, is outside the triangle, but inside the obtuse angle. This will make more sense later. So when the triangle is obtuse, the circumcenter is outside the triangle, but inside the obtuse angle. Here's my obtuse angle, and the circumcenter is inside. And then, Jalen, you said when it's a right angle, you'll have to trust me that, well, I could actually measure that. Measure angle. Ooh, that's pretty close to 90. We'll take it. And you were 100% correct. When it's a right triangle, the circumcenter goes to the midpoint of the hypotenuse. So we can grab any one of these points and drag it around and see where the circumcenter goes. And then that second property I mentioned, we'll get, where's my circle? There it is. It doesn't look like a circle because of the projection, but that is a circle. And again, you see that it goes through all the vertices, and if I drag the triangle, you'll see that it still goes through all the... Can you see that circle, by the way?
Yeah. Yes.
Okay. Here, I think this might help display. Line style. Let's make it medium. That's better. Okay. So there's that circle. And as we drag any one of these vertices, they will always go through the three vertices. So circumcenter is the POC for the perpendicular bisectors. It's the center of the circumscribed circle. We good with that? This leads us to our next center, because we need to talk about angle bisectors. We know what an angle bisector is. It's a line, ray, or segment that splits an angle in half. And so what this says is that if you have a point on the angle bisector of an angle, it's equidistant from the sides of the angle. Remember, way back when, I forget who it was, but somebody burst into flames and ran into the river? Who was it? Oh, Matt, okay. You'll recall that we decided that we need to measure that distance along a perpendicular. So this is the same way that we would measure it here. F is our point on the angle bisector. The distance from the angle would, or sorry, the angle side would be measured along a perpendicular. So therefore, FD would be equal to FE. That's called the angle bisector theorem. If I move F further down the angle bisector, the distances would get smaller, but they'd still be equal. And so, yeah.
So this is true because angle FED is congruent to angle EBF?
Say that again.
It's true because the two angles are congruent, right?
These two angles. Those are the two you're talking about?
Yeah.
Yeah, because it's an angle bisector. And so we could go and do the proof. We'd end up proving the triangles are congruent by hypotenuse leg. And therefore the distance is, well, no, we would use, what would we use? Angle side. So I would prove this top triangle is congruent to bottom triangle, and that would make those always congruent by CP/CTC, but I didn't want to bother with all that stuff and just thought maybe you could trust me. You good?
Yes.
Okay. All right. Now, why did we do this? Because now our next transition to our next center, would be to take all the angle bisectors in a triangle. If I draw all 3 angle bisectors, strangely enough, they form a POC, and that POC is called the incenter. It's the point of intersection between the angle bisectors of a triangle. Here's what's going to cause the biggest problem for you. Notice that this picture looks very similar to the other picture, but it's completely different. I'll explain why in a second. I'll give you a chance to get caught up writing-wise, and then I'll explain how the pictures are different. What time are we out of here?
53.
What time?
53.
You're kidding. Okay. I'm going to pick it up a little bit here. All right, what's changed? In the other picture, we had these being perpendicular bisectors. We don't necessarily know that they're perpendicular bisectors. They're just perpendicular. I'll get to the red segments in a second. The angle bisectors are the green things. So there's the angle bisector of C, of A, and of B, and they meet at that point called the incenter. The reason the red segments are in there is because the second property of an incenter is that it's the point equidistant from the sides of the triangle. So the circumcenter is equidistant from the vertices of the triangle. The incenter is equidistant from the sides of the triangle. So again, this gets back to the Matt bursting into flames and running to the river. If that's Matt at the incenter, he would run along the perpendicular to get to D. Question?
So the red is the perpendicular bisector and the
No. The red is just a perpendicular. In this case, not a perpendicular bisector, just a perpendicular.
Okay, but if it was like if the point D was in the middle of A and C, then that would be the perpendicular bisector.
Oh, does E, D, and P, well, those red lines, are they all equal to each other?
Yes. Because of the third property of an incenter, which is it's the center of an inscribed circle. So circumscribed circle, circle around. Inscribed circle, inside. I'll show you a picture in a second. Oh, well, let's, before I click. Acute triangle, incenter's inside. What if I make the triangle obtuse? Where's the incenter going to go? Outside, good guess. What if it's a right triangle? On, where? Any idea where on? Midpoint of the hypotenuse. Okay, well, let's take a look. Come over here again. Okay, here's the triangle, similar to the one I started before. I show the bisectors. Those are the angle bisectors. They meet at that vertex again, called the incenter. That point is equidistant from the sides of the triangles. So if I wanted to show that, I would show perpendiculars, not perpendicular bisectors, just perpendiculars. And then the last thing is what's called the inscribed circle, which is that guy. So notice now, actually let me hide that for a second. We'll just do this one. Acute triangle, inside. Obtuse triangle, inside. Right, whoops. Right triangle, inside. So the incenter is always inside the triangle. And then the last is the inscribed circle. So that inscribed circle stays inside the triangle no matter how you drag this around. I know your brain's about to explode. It's going to get worse for a little bit, but bear with me. Let's skip that. Well, we'll talk about the example real quick. Notice I've got a whole bunch of triangles in that picture. If that angle's 32, that angle has to be 32 because it's an angle bisector. That angle's 90, we can find those angles. If this is 34, that's 34. We can solve for those angles. If that segment is 15, then we can do Pythagorean theorem because that's 12 to find the red. And remember, all three of the red segments are congruent. All right, so you've got some angle bisector stuff going on there. You got some Pythagorean stuff, theorem stuff wrapped up in that picture. And I know I'm going really fast. I apologize. Okay, that's the first two. Any problems there, or questions or clarifications? And again, I'm going very fast, I apologize.
The world's largest sign.
Second day is the two other centers. The process happens again in that I'm going to introduce you to two new lines, and each of those two lines will form a point of concurrency. So the first one is called a median. Let me define a median first before we get to centroid. A median is a segment that connects a vertex and a midpoint of the opposite side. And I'll say that again for you. A median is a segment that connects a vertex and the midpoint of an opposite side. Everybody get that? Once more. It is a vertex that connects, it is a segment that connects a vertex and the midpoint of the opposite side. Okay, so L is the midpoint of AC. How do I know that? Because I got 3 tick marks on each side. And therefore the median is that line BL. It goes from the opposite vertex to the midpoint. And of course, as you can figure, they would all intersect at the same point, called the point of concurrency, and this one is called the centroid. No extra segments in there, no distances to worry about. It does have some special properties we'll get to in a second. Pretty good with
So
that.
the point of concurrency is where every line meets together.
Where those lines all meet, yes. And that will always be true regardless of the shape of the triangle. That's what makes these things so weird. Special property number 1. The distance, and it's summarized here, but basically the distance from the vertex to the centroid is twice as long as the distance from the centroid to the midpoint.
I have a question. Are these online so we could write them down?
They will be when I'm done.
Okay.
Yeah. Yeah, if you just want to become a mass sponge and just absorb information for the rest of the period, that's fine. I'll put the slideshow and the video both online when we're done. Okay? So again, the distance from the vertex to the midpoint, the distance from the vertex to the centroid is twice as long as the distance from the centroid to the midpoint. BP is twice as long as PL. AP is twice as long as PK. All right, acute triangle. Question.
So would JP be PC to PC?
No. JP would be half PC, or PC is twice JP. This is the smaller one. This is the bigger one. Okay. Third property of a centroid. This is kind of weird. It doesn't have a very big application for us, but it's the balancing point of the triangle. If I cut this triangle out of the smartboard, I could balance it on my finger at P. Okay. Also known as the center of gravity. Okay, acute triangle, the centroid's inside. What happens if I make it an obtuse triangle? Where's the centroid going to go?
Inside.
Stays inside?
Yeah.
All right, what if I make it a right triangle?
Stays inside.
Stays inside. So you guys are gun shy after the whole incenter thing where you want to go inside, inside, inside?
Yeah.
All right, let's find out.
They're all moving outside.
Inside, inside, inside. Okay, can't get the centroid outside. Not real exciting. And the last one is even less exciting. Okay, fourth line. We'll do the line first, then we'll talk about the center. The fourth line is a perpendicular. Okay. That's also going to cause some confusion because you're going to get perpendicular bisector confused with perpendicular. Perpendicular just means it forms a right angle. Here's my right angle. So I took this vertex and I dropped what's called an altitude down to the other side. And the only thing that does is it forms a right angle. That's it. There's no perpendicular bisecting. There's no cutting anything in half. It's perpendicular. That's it. Again, that's called an altitude. You take all three triangles, I'm sorry, you take all three altitudes in a triangle and they meet at a point called the orthocenter. The orthocenter has no special properties. It's not the center of any circle, it's not any weird distance, it's just the orthocenter. Okay, there's an acute question.
I was just curious about homework. So like for a homework problem, would we have to find like orthocenters and and like and stuff like that, or would we have to find like degrees?
That's an excellent question. Can I answer it when I'm done? Because I'll tell you where we're gonna go from here.
Okay.
Okay,
For the median, what was the circle called?
there is no circle for the median.
Oh,
No. Acute triangle, orthocenter's inside. What if it's obtuse?
Inside.
Inside and right triangle?
Inside.
Inside. Okay, so you guys are all, you bought into the inside thing ever since you got burned the one time. Okay, there's the orthocenter. Uh-oh. Okay, so this is what you want to make a note of. For the orthocenter, when it's an obtuse triangle, it's outside the triangle, but behind the obtuse angle. So remember, the circumcenter is outside, but inside the obtuse angle. This is outside, but behind the obtuse angle. And what happens when it's right? It's on the vertex of the right angle, correct. Here's going to be the biggest problem. I have just assaulted you with tons of information. Each individual center, you need to know what lines created that center. What's that center called? What are all the special properties of all those centers? And it's going to be a little crazy for a little while until you get that burned into your brain.
Wait, what was acute?
Acute is inside. All four, if it's acute, it's inside, which is kind of nice. The only time it gets weird is when you do obtuse or right triangle. Okay, so where are we going to from here? This is how the rest of this chapter plays out, is eventually, well, I shouldn't say eventually, tomorrow you're going to be working on homework that's going to ask you some generic questions about it. It's going to be examples of which center is this? Okay, picture of a triangle, which center is this? You'll do some Pythagorean theorem. You'll do some application stuff with some of the angles in a triangle, that kind of stuff. Getting familiar with the four different centers. Eventually what we're going to do is drop a triangle on a coordinate plane. And this is where things are going to get ugly. We take a triangle, we know three vertices, we put it on a coordinate plane. You're going to be calculating the locations of the centroid, the circumcenter, the orthocenter, and the incenter. That's going to get ugly. Okay? But we're going to build up to that. I'm not saying that the first stuff that we do is going to be real easy. It's going to be confusing, and eventually you'll get it. But it's going to take a little bit of work to get there. And then when you do get there, then we start with the fun algebra stuff. Okay? So tonight, just chill. You're fine. Don't do anything. Just forget about geometry for a night. Tomorrow, I will post both assignments.
every day?
When you come in, you'll be working on those two assignments. You can work with a partner, work with a small group, work by yourself, I don't care. I'll also post a summary sheet which takes most of the stuff that we talked about in here and puts it onto one nice little sheet. I'll also post the video and the slideshow. Kira, question?
So if the first picture a perpendicular bisector and a perpendicular, is that perpendicular bisector like actually goes through the midpoint of the bisector?
Perfectly said. Okay, anything else? Everybody clear with what's going to happen tomorrow? All right, so whatever you don't get done in class tomorrow will be homework over the weekend. It shouldn't be that much because you'll have a good 15 minutes to work on that homework tomorrow. Okay? Beautiful.